Ever wonder how your phone knows exactly where you are? Like weaving you through traffic with GPS magic?
Yeah.
That's state estimation in action, using measurements to figure out the state of a system.
Right.
And you've sent over a whole stack of sources on this.
Yes.
So we're diving deep into the world of state estimation today.
Okay.
We'll journey through its history, explore the different types and the popular filters used, and even compare it to all the buzz around machine learning.
What's fascinating is that state estimation, it isn't new.
Oh, okay.
It's been around for centuries.
So my phone's navigation superpowers, they have ancient roots.
Yeah.
That's wild.
It is.
The presenter's notes mention a guy named Gauss. What's his connection?
Carl Friedrich Gauss, a mathematical whiz kid,
Mm.
developed the least squares method
Okay.
back in 1795 when he was just 18.
Wow.
It revolutionized how we get the most accurate estimate from a bunch of measurements,
Right.
especially if those measurements have errors. It was a game changer for astronomy, helping scientists pinpoint the orbits of planets with much more precision.
Hold on, you're telling me the foundation of my GPS, the thing that gets me into my morning coffee,
Yeah.
was laid down centuries ago by a teenager who loved math.
Yeah.
That's mind-blowing.
It is amazing.
So from planets in the sky to my pizza delivery, it all started with Gauss and his least squares method.
Precisely. And that method became the foundation for many of the filters we use in state estimation today.
Okay.
It evolved over time, leading to techniques like the Wiener filter in the 1940s. Then in 1960 came the Kalman filter, which truly revolutionized the field.
This is where things get really interesting, right?
Yeah.
The Kalman filter helped land astronauts on the moon during the Apollo missions.
Yes.
Talk about high stakes.
Absolutely. The Kalman filter was crucial for navigating the Apollo lunar modules, proving its ability to estimate a system's state in real time with incredible accuracy. And it's not just space travel. The Kalman filter is everywhere, from aerospace engineering to economics.
Okay, history lesson absorbed. But what exactly are the different types of state estimation? The presenter's slides mention filtering, smoothing, prediction, and inference.
Right.
Let's start with filtering, which you said is how GPS works.
Right. Filtering is all about figuring out where something is right now using the measurements we have up to this point.
Okay.
Imagine tracking a moving target in real time. You're constantly getting new data and updating your estimate of the target's location.
Right.
Filtering methods are designed to handle the challenges of this real-time processing.
So if filtering is about the now,
Right.
what's smoothing all about?
Okay.
Is it like filtering with a superpowered magnifying glass?
Not quite. Smoothing focuses on refining our understanding of the past.
Oh, okay.
Think of your tracked GPS route after a hike.
Okay.
Smoothing uses all the data, including points after a specific moment,
Right.
to get a more precise picture of where you were at that moment.
So it's like going back and editing your GPS track for accuracy after the fact.
Yes.
I see how that could be useful for analyzing past events. What about prediction? That seems pretty straightforward, like trying to guess what happens next.
Exactly. Think of weather forecasting.
Yeah.
You're using past weather data to predict what the weather will be like tomorrow or next week. That's prediction in a nutshell, using what we know to anticipate the future. But remember, prediction always involves some uncertainty. The further out you predict, the less certain you become. Just think about those long-range weather forecasts. They're often less accurate than the short-term ones.
That makes sense, like trying to predict where a billiard ball will go after a complex shot.
Exactly.
Okay, we've covered filtering, smoothing, and prediction. What about this inference thing? Sounds a bit like we're getting philosophical.
Inference is a broader term, encompassing all the types we've discussed so far.
Oh, okay.
Filtering, smoothing, and prediction.
Okay.
It's about drawing conclusions about a system based on available information,
Right.
even estimating the parameters that govern the system's behavior, like system identification,
Okay.
using data to understand how a system works internally.
So it's the umbrella term, the big boss of state estimation.
Exactly.
We've got these different ways to estimate a system's state,
Right.
and they all fall under this inference umbrella. But to actually do this estimating, we need tools, right?
Yes,
What are these famous filters everyone keeps talking about?
that's right. Each type of state estimation often uses a specific filter to do the heavy lifting.
Okay.
And the first one we absolutely have to discuss is the legendary Kalman filter.
And I've heard of the Kalman filter. Apparently even Kalman himself didn't expect it to be so widely used.
Yeah.
Why is that?
It's incredibly efficient,
Hmm.
which is perfect for real-time applications where speed is key.
Right.
But it does have its limitations. The Kalman filter works best for linear systems, where the relationship between input and output is a straight line, and it assumes that the noise in your measurements follows a Gaussian distribution, that familiar bell-shaped curve.
Just straight lines and bell curves. Got it.
Yes,
But what happens when things get a bit more wiggly?
right.
What if the system isn't linear?
That's where the extended Kalman filter, or EKF, steps in.
Okay.
It's the go-to for handling nonlinear systems.
I'm picturing a roller coaster instead of a straight line now.
Yeah.
What does nonlinear actually mean in this context?
Think of a simple pendulum swinging back and forth. The relationship between its angle and its speed isn't a straight line, it's a curve.
Right.
The EKF handles these curvy nonlinear systems using a trick called linearization.
So it's like taking that curve and pretending it's a bunch of tiny straight lines connected together.
Exactly.
Clever.
The EKF breaks down the nonlinear problem into smaller linear chunks it can handle. It's not perfect, but it's widely used in fields like robotics and navigation, which I know you find interesting.
That's super cool. But what if even the EKF can't handle the complexity?
Right.
Is there an even stronger tool in our state estimation arsenal?
There is the unscented Kalman filter, or UKF. And don't worry, the unscented part has nothing to do with deodorant.
Hold on, I thought we were talking about math, not personal hygiene.
Yeah, I know.
Okay, so what makes the UKF so special?
It's another way to handle nonlinearity,
Okay.
but it has a unique advantage.
Okay.
The UKF uses sigma points
Yeah, okay.
to represent the probability distribution of the system's state.
Right.
It's a more sophisticated approach than the EKF, and it can often achieve higher accuracy, especially for systems with strong nonlinearity.
So the UKF is like the EKF's smarter sibling,
Yeah.
but maybe a bit more of a resource hog.
Possibly.
I'm sensing a theme here. As the complexity of the system goes up, we need more powerful filters.
That's right.
But what if even the UKF isn't enough? What if the system is so complex and unpredictable
Yeah.
that we can't even define its behavior with equations?
That's when you look at a particle filter.
Okay, I'm intrigued. What's so special about the particle filter?
Imagine a swarm of possibilities, each representing a potential state of the system.
Okay.
These are our particles.
Mm-hmm.
The particle filter uses these particles to explore the entire probability space of the system.
Wow.
It's like having a team of tiny explorers, each checking out a different possibility.
Whoa, that's a cool visual. So the particle filter is the ultimate explorer, capable of handling even the most chaotic system.
Exactly. It's particularly good at handling highly nonlinear systems and situations where the noise isn't Gaussian.
Right.
It can even handle the kidnapped robot problem, where a robot suddenly loses its position,
What?
like a self-driving car going through a tunnel and losing its GPS signal.
Wait, a kidnapped robot? That sounds like a plot from a sci-fi movie. But seriously, how does the particle filter solve that?
It can quickly adapt and re-estimate the robot's position, even with a sudden jump in the measurements.
Wow.
It does this through resampling, where particles closer to the actual state get duplicated,
Okay.
while those that are far off get eliminated.
Survival of the fittest for these particles, huh?
Exactly.
Only the best guesses survive.
So we've got our lineup of filters: Kalman filter, EKF, UKF, and the mighty particle filter.
Right.
But how do we know which one to choose?
All right.
Is there a filter flow chart to help us decide?
There is. But before we get to that, it's important to understand the strengths and weaknesses of each filter. Let's unpack those first, and then we can dive into the decision-making process.
Okay, I'm ready for our filter pros and cons list. Lay it on me.
Let's start with the Kalman filter.
Okay.
Its simplicity and efficiency are its superpowers. It's perfect for linear systems with Gaussian noise. It's well understood theoretically.
And it's relatively easy to implement. But remember those limitations.
Yeah.
It can't handle non-linearity or non-Gaussian noise, and it struggles with situations where there are multiple likely states for the system.
So Kalman filter, great for simple systems, not so much for complex ones.
That's right.
What about the EKF? What are its winning qualities and fatal flaws?
The EKF's biggest advantage is its ability to handle nonlinear systems.
Okay.
It's also relatively efficient compared to some other nonlinear filters, but it can sometimes become unstable if the nonlinearity is too strong.
Right.
And it requires a more complex calculation that can be computationally expensive.
So a bit more temperamental than the simple Kalman filter?
Yes.
And what about the UKF? How does it compare?
The UKF can handle stronger nonlinearity than the EKF
Okay.
and doesn't require that complex calculation.
Right.
This often leads to better accuracy.
Mm-hmm.
However, it comes at a higher computational cost
Right.
and still assumes a single most likely state for the system. Tuning its parameters to get the best performance can also be a bit tricky.
Okay. UKF, good for those tricky nonlinearities,
Yeah,
but more demanding computationally and a bit picky.
that's right.
And lastly, our champion of flexibility, the particle filter. What are its superpowers and its kryptonite?
The particle filter's strength is its flexibility. It can handle pretty much any nonlinearity, works with non-Gaussian noise, and can represent situations where the system might have multiple likely states. However, it can be very computationally expensive,
Right.
especially when you need many particles to accurately represent the system's state.
Yeah.
And it's susceptible to something called particle degeneracy,
Oh,
where all the particles end up clustered in one spot,
okay.
which can lead to inaccurate estimates.
Particle degeneracy. That sounds a bit like a black hole swallowing up all the possibilities.
It's a good analogy. It's something to be mindful of when using particle filters.
All right, so we've got a good grasp of the pros and cons of each filter.
Right.
Now for the million-dollar question, how do we actually choose the right filter for a specific problem?
Right.
Is there a secret handshake or something?
Not quite a secret handshake,
Okay.
but the presenter's notes have a helpful decision-making framework.
Okay.
It boils down to 3 key factors:
Okay.
the characteristics of the system,
Okay.
the computational resources available,
Okay.
and the accuracy requirements of the application.
Okay, let's break those down. What do we need to know about the system itself?
First, we need to determine if the system is linear or nonlinear.
Okay.
Remember that straight line versus wiggly line test?
Yes.
If it's linear, the Kalman filter is often the best choice.
Okay.
If it's nonlinear, we need to consider how strong the nonlinearity is.
Right.
If it's mild, the EKF might suffice. If it's strong, the UKF could be a better option.
Got it. Straight lines, Kalman filter, wiggly lines, EKF or UKF, depending on how wiggly they are.
Right.
What else do we need to consider?
We need to figure out if the noise in our measurements follows a Gaussian distribution or not.
Okay.
If it does, we're good with the Kalman filter, EKF or UKF.
Okay.
But if the noise is non-Gaussian, the particle filter might be the only way to go.
Okay.
And we also need to consider if the system might have multiple likely states at any given time.
Right.
If so, the particle filter is usually the best option.
Right, because the other filters assume a single most likely state.
Exactly.
So we analyze the system,
Right.
figure out its linearity,
Right.
noise characteristics,
Right.
and the potential for multiple likely states.
Right.
What's next?
Then we need to think about our computational resources. Do we need real-time performance?
Okay.
What's our processing power like? How much memory do we have?
Right, because some filters are more computationally expensive than others.
Right.
The Kalman filter is the most efficient. The EKF is next. The UKF is more demanding. And the particle filter is the most resource intensive, right?
Exactly. We have to balance the complexity of the filter with the capabilities of our hardware.
And the last factor is the accuracy requirements, right?
Yes,
How much precision do we need for our state estimates?
that's crucial. Can we tolerate some uncertainty, or do we need pinpoint accuracy?
Right.
If we need the highest possible accuracy and can handle the computational load, the particle filter might be the way to go.
Okay.
But if we're okay with some margin of error and need a faster solution,
Yeah.
we might opt for one of the other filters.
It's all about finding the right balance between accuracy, complexity, and computational resources.
Exactly.
This is a lot to keep in mind. Is there a cheat sheet to help us choose the right filter?
The presenter's notes have a quick selection guide, but remember, it's just a rule of thumb.
Yeah.
As a general guideline, if you have a linear system, the Kalman filter is your go-to.
Okay.
If you're dealing with mild nonlinearity, the EKF is a solid choice. Strong nonlinearity calls for the UKF. And when you have those complex distributions or really unpredictable systems, the particle filter is your best bet.
That's a handy framework to have.
Yes.
But before we wrap up this part of our deep dive, I'm curious about something.
Okay.
We've been talking about state estimation,
Right.
but there's this other big trend in technology right now, machine learning. How do these two approaches compare?
Okay.
Are they friends or foes?
That's an excellent question. They might seem like separate worlds, but they have more in common than you might think.
Okay.
And they can actually work together quite powerfully.
Okay, color me intrigued. Tell me more.
At their core, state estimation and machine learning have distinct approaches.
Okay.
State estimation is model-based.
Mm-hmm.
It relies on having some knowledge of the system's underlying physics or dynamics.
Okay.
Think of those equations that describe how a pendulum swings or how a rocket flies.
Look.
We need those models to make our state estimates.
Okay.
Machine learning, however, is data-driven. It's all about learning patterns from data,
Right.
often without needing explicit models.
Okay.
Think of those image recognition algorithms
Yeah.
that can tell a cat from a dog just by analyzing thousands of pictures.
So state estimation is like a scientist carefully studying the rules of the game before making predictions.
Yeah.
Machine learning is like an artist who learns by observing and imitating,
Right.
rather than studying the rules of perspective and anatomy.
That's a good analogy.
Interesting.
This difference in approach leads to other distinctions.
Okay.
State estimation is often used for real-time processing,
Okay.
where we're constantly updating our estimates as new measurements come in.
Mm-hmm.
Think GPS navigation, where your position is constantly being updated as you drive.
Right.
Machine learning, on the other hand, is often used for offline processing,
Okay.
where we train a model on a large data set
Mm-hmm.
and then use it to make predictions on new data.
So state estimation is the sprinter reacting in the moment. Yeah.
Machine learning is the marathon runner, training on past data to perform well in the future.
Yes.
But you said they can work together.
Yes.
How does that work?
Absolutely. There's a growing trend of combining these two approaches,
Okay.
creating hybrid solutions that leverage the strengths of both. For example, machine learning can help improve the parameters of state estimation filters,
Okay.
making them more adaptive and robust.
So machine learning can help fine-tune those filters to perform even better.
Right.
Are there any specific examples of how this is already happening? I'd love to hear more about that.
There are some really exciting examples, and that's exactly what we'll pick up in part 2 of our deep dive.
Sounds like a plan. Stay tuned, folks. We'll be right back with more on the fascinating world of state estimation.
Discuss good.
Welcome back. We've covered a lot of ground exploring the history and types of state estimation, the popular filters used, and even how it compares to machine learning. But I'm ready for more. Great, because now we're going to see just how pervasive state estimation really is.
Okay.
We keep mentioning GPS,
Right.
but its applications go way beyond navigation.
Yeah, I'm really curious to hear about those other applications. What else can state estimation do?
Let's take robotics, for instance. One of the papers you sent by MedHat talks about using multiple portable devices, like smartwatches,
Okay.
for enhanced misalignment estimation in portable navigation.
Okay, break that down for me. What's misalignment estimation in this context?
Imagine a robot arm trying to grasp an object.
Okay.
It needs to know the object's exact location relative to its own position.
Right.
Any misalignment could mean a fumble.
Right. So state estimation helps the robot accurately determine its own position and orientation.
Right.
But how do smartwatches help with that?
This paper suggests that using multiple sensors, even ones we wear,
Mm-hmm.
can lead to much more accurate estimations. It's like giving the robot extra eyes to see its surroundings.
That's brilliant. And it totally makes sense considering how popular wearable tech has become. What other fields rely on state estimation?
Let's shift gears to aerospace,
Okay.
where precision is absolutely crucial. We already talked about the Kalman filter's role in the Apollo missions, but state estimation is vital for all modern spacecraft and aircraft.
I can imagine those systems are operating in incredibly complex environments.
Yeah.
How does state estimation help?
Think of a satellite orbiting Earth.
Okay.
Gravity, atmospheric drag, and even solar radiation constantly affect its position and velocity.
So it's like a celestial balancing act
Yeah.
with state estimation keeping everything in check.
Exactly. State estimation algorithms use sensor data to constantly track the satellite's state, making sure it stays on course and completes its mission. And those same principles apply to aircraft navigation too, especially with the rise of autonomous drones.
It's amazing how a mathematical concept can have such a huge impact on real-world systems. What other examples are there?
Let's dive into a field you might not expect.
Hmm.
Finance.
Finance. I wouldn't have guessed state estimation plays a role there. How does that work?
Finance is all about understanding and predicting market behavior.
Right.
Stock prices, interest rates, currency exchange rates. They're constantly fluctuating.
Sounds like a lot of unpredictable, wiggly lines.
Exactly. State estimation is used in algorithmic trading,
Sure.
risk management, and portfolio optimization.
Okay.
By applying these techniques, financial analysts try to extract signals from noisy market data, helping them make better decisions.
So it's like having a secret weapon to navigate the complexities of Wall Street.
You could say that. But let's not forget one of the most relatable applications of state estimation, weather forecasting.
Yes, the classic example of prediction in action.
Right.
We all rely on weather forecasts every day.
And those forecasts rely heavily on state estimation.
Right.
Meteorologists use sophisticated models that incorporate data from satellites, weather balloons, ground stations, and more. They're essentially trying to estimate the state of the atmosphere.
So they're figuring out things like temperature, pressure, humidity, and wind at different points in the atmosphere, using that to predict how the weather will evolve. It's mind-boggling how much data and computation goes into generating those forecasts.
It is. And as computing and data assimilation techniques advance, weather forecasts are becoming even more accurate.
It's incredible how this one concept, state estimation, has found its way into so many different fields. It really highlights the power of mathematical tools to solve real-world problems.
Absolutely. And as we move forward, especially with AI and machine learning, I think we'll see even more innovative applications emerge.
You mentioned earlier that machine learning and state estimation can work together.
Right.
Do you have any specific examples of how that's already happening?
One exciting area is autonomous driving. Self-driving cars depend heavily on state estimation to understand their surroundings, track other vehicles, and plan routes.
Right. It's like giving the car a sense of where it is, where everything else is, and where it needs to go.
Precisely.
Yeah.
Traditional state estimation techniques, like the Kalman filter, are still crucial in many autonomous driving systems.
Okay.
But they're increasingly being enhanced by machine learning algorithms that can handle more complex scenarios.
It's like having a skilled driver who's also constantly learning and improving.
Yeah.
What sort of things can machine learning add to the mix?
For example, machine learning can be used to improve the accuracy of object detection and tracking, to predict the behavior of other drivers, and even to adapt the car's control systems to different road conditions.
Right.
It's not just about knowing where things are, but also anticipating what they might do next.
That's where machine learning really shines, in that predictive capability. It can analyze huge amounts of driving data to anticipate hazards, react to surprises, and ultimately make driving safer and more efficient.
Exactly. It's a powerful combination. State estimation, providing the foundation of location and motion tracking, and machine learning adding intelligence and adaptability.
So it's not just limited to self-driving cars?
Not at all. This fusion is also happening in robotics, where robots are becoming more adept at navigating complex environments and interacting with humans. And we're seeing it in healthcare, where state estimation and machine learning are being used to monitor patients, diagnose diseases, and personalize treatment plans.
It's amazing to think about the possibilities. As these technologies keep evolving, I'm sure we'll see even more creative and impactful applications.
I completely agree.
This brings us back to a key takeaway from Ms. presentation. State estimation is not a static field. It's constantly evolving, adapting to new challenges, and embracing new technologies.
Exactly.
It's like a living, breathing set of tools that's constantly being refined and expanded. What stands out to you most about the world of state estimation?
For me, it's the sheer breadth of applications. It goes way beyond GPS and navigation, impacting so many aspects of our lives. It's a testament to the power of fundamental mathematical concepts to pop up in the most unexpected places.
Absolutely. Now, before we move on to the final part of our deep dive, what's next on the agenda?
In our final part, we'll delve into the future of state estimation. We'll examine the challenges and opportunities ahead. And explore how this field is poised to shape the world around us in the years to come.
Welcome back to the final part of our deep dive into state estimation. We've explored its history, the different types and filters, and seen how it's used in fields from aerospace to finance. Now it's time to look ahead to the future of state estimation.
It's an exciting time for this field. As with any technology, the pace of change is rapid. And one trend that's really taking off is the integration of state estimation with artificial intelligence, especially machine learning.
We've talked about that a bit already, but I'm eager to dive deeper. What are the biggest challenges and opportunities that this integration presents?
One challenge is the ever-growing complexity of the systems we're trying to estimate.
Right.
As we build more sophisticated machines like self-driving cars and collaborative robots, those systems become more intricate.
Yeah.
It's not just about tracking one object anymore.
Right.
It's about understanding a whole network of interacting parts.
That makes sense.
Yeah.
Our trusty Kalman filter might struggle to keep up with that level of complexity.
It might.
So how does machine learning help?
Machine learning excels at finding patterns in vast amounts of data.
Okay.
Even patterns our traditional models might miss.
Right.
For example, in robotics, machine learning can help predict human movements in a shared workspace.
Okay.
This allows robots to anticipate potential collisions
Right.
and plan their actions accordingly.
That's crucial for safety and smooth collaboration between humans and robots.
It is.
What about in the world of self-driving cars?
In autonomous driving, machine learning can predict the behavior of other vehicles, pedestrians, and cyclists,
Okay.
which is essential for navigating busy city streets.
Right.
It's about moving beyond just reacting to what's happening right now and starting to anticipate what might happen next.
That predictive capability is key for truly autonomous systems.
It is.
But I imagine merging these different approaches, the model-based world of state estimation and the data-driven world of machine learning presents some challenges.
It does.
How do researchers tackle that?
One approach is to use machine learning to actually improve the models we use in state estimation.
Okay.
It's like teaching our models new tricks.
Right.
For example, we can use machine learning to learn the parameters of a Kalman filter, allowing it to adapt to the specific characteristics of a system.
So instead of relying on fixed parameters, the Kalman filter becomes a student, constantly learning and improving.
Exactly.
That's a really cool idea.
It is.
But what about the need for tons of data to train these machine learning models?
Yeah.
Where does all that data come from, especially in specialized areas like robotics?
That's a valid point.
Yeah.
Data can be scarce or expensive to collect.
Right.
One solution is to use simulations to generate synthetic data,
Okay.
which can supplement real-world data. Another approach is transfer learning,
Okay.
where we train a model on a large data set from one domain
Right.
and then fine-tune it on a smaller data set from a related domain.
So it's like taking the knowledge learned from analyzing a million images of cats and dogs and applying it to recognizing different breeds of horses.
Exactly.
That's a neat trick.
Transfer learning allows us to make progress even when data is limited.
It's fascinating to see how these different areas are coming together to shape the future of state estimation.
It is.
And as we look ahead, I think we'll see the lines between state estimation, machine learning, control theory, and optimization becoming increasingly blurred. We won't just be estimating the state of the system anymore.
Right.
We'll be using that information to make intelligent decisions and control how the system behaves.
Exactly.
It's like we're witnessing the birth of a new generation of intelligent systems.
Yeah.
Systems that can sense, think, and act in the world. It's both exciting and a little bit daunting.
It is. That brings us back to that thought-provoking question from MedHack's presentation.
Okay.
Considering how quickly AI and machine learning are advancing, how do you think state estimation will change in the years to come?
Wow.
What new applications do you envision?
Wow, that's a big question.
It is.
I'm no expert, but I think the integration with machine learning will be huge. We'll see more hybrid systems that can learn, adapt, and make decisions in complex, unpredictable environments.
I agree.
I think this will lead to breakthroughs in areas like robotics,
Yeah.
where robots will become more collaborative, intuitive, and capable of working alongside humans on a wide range of tasks.
I think so too.
And maybe we'll finally see truly self-driving cars that can handle any road, any weather condition, safely and reliably.
That would be amazing.
Those are exciting possibilities.
They are.
And beyond robotics and self-driving cars,
Yeah.
I think state estimation will play an even bigger role in personalized healthcare, smart cities,
Right.
and space exploration.
Absolutely.
It's incredible to think that this idea, which started with studying the stars centuries ago, could have such a huge impact on the future.
It really is a testament to human ingenuity and our constant drive to learn and explore.
It is.
As we wrap up this deep dive, I encourage you to keep exploring, keep questioning, and keep pushing the boundaries of what's possible.
It's been an amazing journey. I'm walking away with a whole new appreciation for the hidden world of state estimation.
Me too.
To everyone listening, thanks for joining us on this deep dive. Keep those brains engaged and never stop learning.